Welcome everyone to this brown bag. My name is Katinka. I'm a lead data scientist at ELISA. And last year I had the pleasure of working with gravitational wave researchers on using machine learning techniques and applying them to do gravitational wave science. And today I'm here to tell you all about it. So first I will tell you a little bit about the background, what are gravitational waves, and how this whole project came about, what we initially set out to do in this project. So talking about the glitch classification model that we created. And finally, the best part, which was the generation of synthetic noise or glitch images using generative adversarial networks. So what are gravitational waves? Well, gravitational waves were first predicted by Albert Einstein in 1916 on the basis of general relativity theory, and they were first confirmed by observations in September of 2015. The observations were made by the LIGO observatories, and these observations matched the signal that would be emitted by the merger of two black holes, as illustrated here in this video simulation. Now, gravitational waves are basically ripples in space-time caused by the inward spiraling motion and merger of two black holes. So you can also see the space-time distortions as the light from the stars behind the black holes are being distorted, and they seem to be moving around in this video. OzGrav is the Center of Excellence for Gravitational Wave Research in Australia, and towards the end of 2021, ELISA formed a partnership with OzGrav with the goal of enhancing machine learning and the application of artificial intelligence in gravitational wave astronomy. And the specific focus of our project was to carry out glitch classification using gravitational wave data. So what are these glitches that I keep talking about? Well, here on the left, you can see the LIGO observatory, and these long arms here are the interferometers that detect gravitational waves. And what is important to note here is that these are very sensitive detectors. So gravitational wave signals are very faint in general, and that's why we need very sensitive detectors, which are really great for catching the weak signals, but it also makes the detectors susceptible to picking up all kinds of instrumental and environmental noise transients. And these disturbances are what we call glitches, which kind of look like the features on the right. And if you Google what causes these glitches, this is one of the first things that comes up. So basically droppings from birds disturbing the observations, but really anything from human activity, trucks driving by, even tidal effects can cause problems. And this is an issue because actually glitches come at a significant rate, and they can mimic gravitational wave signals. So they really are just an unwanted noise in the data. And this is why the Gravity Spy project came to life. So Gravity Spy is an effort to classify the glitches into morphological families by combining the strength of machine learning algorithms and also the effort of citizen scientists. So basically anyone can sign up and contribute to classifying these glitches. And this is important because once we are able to classify these glitches into different categories, this might help to identify the root cause of glitches, but it can also help with mitigation efforts. So, for example, you can imagine a pipeline that is able to automatically detect and remove these noise features from the data. Well, really, that would be the ideal outcome and the end goal of this exercise. So here on the left side, I'm showing you 22 different glitch types that we know exist today. And then the bar chart is showing that some glitches are actually very frequent. So for example, we have more than 7,000 examples of blips. So this is a glitch category. But also there are some which contain less than 100 examples. So there is a 2 orders of magnitude difference between these two numbers. And this uneven distribution is what we call class imbalance. And class imbalance is a problem for machine learning algorithms because if we want to teach an algorithm to predict glitch class, then the algorithm has to see many examples in order to learn what those glitches look like. Otherwise, if there are only a few examples, we might not be able to predict them with a high enough accuracy. And this means that a classification algorithm might not work well on the lower end of this distribution. And there have been previous attempts in the literature to carry out glitch classification. So in a paper published by Behadini, they created a glitch classification model and reported that their model is able to predict the class or the morphology of a glitch with a 98% prediction accuracy. However, what you can see here is the confusion matrix, which is expressed in percentages. And the way you can read this is that we have the 22 different glitches on the X and on the Y axis, and then we have the diagonal line, which is showing the percentage of correct predictions. So in a way, you can think of this as an accuracy matrix. And the point that I'm trying to make here is that even though the overall accuracy is 98%, if we break it down class by class, in some cases, the accuracy is a lot worse. So for example, wandering line is only 14%, which is really low. And this is likely due to the class imbalance that exists in the data. So due to this small sample size, some class accuracies will lag behind. However, class imbalance is not addressed in the paper, and this is something that we are going to talk about today in relation to our project. And this brings me to what we have done together with OzGrav in terms of glitch classification and generative adversarial networks. In our work, we used the Gravity SPY data, but our selection was slightly different than Behadini's because we did some additional data cleaning and training data selection in our work. And our approach was to create 3 different models that are able to morphologically classify these glitches. So we created a logistic regression, an XGBoost model, and also convolutional neural networks. And I won't go into detail on what these are. I will just talk about our best model, which was the CNN. So first we tested our model on the imbalanced data as it is. And then we also did some over and under sampling, meaning that we correct for this imbalance. And we tried to bring the classes to a more similar level to each other. And then we also created synthetic glitch images using generative adversarial networks. And I'm really excited to show you our results today. But first, as I was mentioning, we use different algorithms to create a glitch classification model. And convolutional neural networks gave us the best results here. So here in this table, we have the results, and you can see that we achieve a 95% prediction accuracy for the CNN. And then on the right side is our confusion matrix, showing similar results to what we have seen before, in the sense that the prediction accuracy for some of the classes are high, while the others are much worse. And to remind you again, this is because of class imbalance. So some examples will be more accurate than others due to the uneven class distribution of the data. So we are going to address this by over and under sampling. So we want to bring the data distribution to a slightly more even level. And if you pay attention now, this is what we did. So what happens here is that we set the minimum sample size to be 1,000, and then we oversample the tail of the distribution by duplicating the samples until they reach this limit of 1,000. Then on the other side, we set the upper limit to be 2,400, which is actually pretty much the natural upper limit in the data. And only for the blip category, we allow more examples into the sample, because really this is the largest category by far, and we want to have a high accuracy for this class. And we found these numbers by experimenting with different thresholds. We also tried just bringing everything to the same level, but we found that by using these limits and keeping a ratio of about 2, we found that we can achieve really good results, and we don't have to do anything more dramatic than this. So now the question is, how do the results of classification change after we do over and undersampling? So for the CNN, we achieve a 3% improvement in accuracy. And remember, before it was 95%. And when we break the data down by class, everything looks a lot more even, with more than 90% accuracy for each class. So this is looking much better than before. And I just wanted to show this very quickly to technical-minded data scientists who will want to know about other metrics. So we can also look at the precision, recall, F1 score, and they are looking good as well. In general, all measures are above 90% or so. So this is what I wanted to tell you about classification. And actually, this brings me to the next part of our project, where we will talk about generative adversarial networks, or GANs. So GANs are used for creating synthetic images that mimic real life. And a famous example is StyleGAN, which project has generated realistic-looking faces. So in this image here, these people are not real. They are all AI generated. And in our project, we wanted to use GANs to generate synthetic images of glitch data, mainly because, as we talked about it before, some of our data samples are limited, and if we had larger sample sizes, then this could help with mitigation efforts. So how do GANs work? Well, this is an example of a GAN architecture where we have a generator and a discriminator, which are just deep neural networks. And the way the GAN works is that first the generator creates fake images of something that you're trying to model. So in our case, the glitches. And then we have the discriminator, which checks how good the synthetic images are by comparing them to the real images. And then training happens through a feedback loop. So as you can imagine, designing this whole architecture, so designing a GAN, is a lot of work. But fortunately, we didn't have to create a GAN from scratch, because there are readily available frameworks online. So for example, TorchGAN. TorchGAN is a PyTorch-based framework. So you just have to plug in your data. You can change the architecture if you want to, because you have access to the source code, or you can just leave it as it is. So it's really simple to use. And we actually trained 22 different TorchGAN models for our 22 different glitch types. And now you at home or in front of your computer, you're going to help me decide how good these images are, because we are going to do a quiz. So I want you to have a look at the images on the left and on the right and choose which ones you think are fake. So I will give you a few seconds and decide in your head which ones are fake, images on the left or images on the right. So let's reveal the truth. Well, the images on the left are fake. So if that's the one you choose, then you are correct. Congratulations. But I think we can all agree that the results are looking pretty good and realistic. And we actually created similar images for all 22 glitch types. And we have a few more examples here for more complex morphologies. So these categories are called koi fish, scattered light, wandering line, and low frequency bursts. And even these more complex morphologies can be reproduced by GANs, and this is really exciting. And then finally, in order to check how good our results were, we did the following test. So first, we generated 100 synthetic images for each glitch type. And then we used the previously trained classification model, so our CNN, to infer what classes the synthetic images belong to. And our reasoning here is that if we generated images that are realistic, then the model should be able to predict what class they belong to. And the results are presented here in the confusion matrix. And this is looking really promising. So the glitch types are predicted at a more than 90% accuracy in all cases. And this is a testament to the goodness of the synthetic images, but also the goodness of the classification model. And actually, this brings me to the end of the presentation. But before I say goodbye, I wanted to mention that this project actually resulted in a paper that is now published in the Classical and Quantum Gravity Journal. So feel free to check out that paper if you are interested in the details of the project. But otherwise, thank you so much for listening, and I really hope you enjoyed this presentation.